Let's focus on a couple extra items that we can do to start identifying some relationships around our arc length, our radius, and the central angle that we build. And so what you see here is the same diagram as before, except now I've shaded in this little area, this slice of the pie, if you'd like. And this little area is going to be called, this shaded area is called a sector. It's a sector of the circle. It's a part of the circle. And what we're going to start to do is realize that there's an interrelationship between these various variables, our angle, our radius, and our arc length, as well as the area of this particular sector. So what we're going to do first, we're just going to do a little bit of review. And if I said what formula represents the area of a circle, you would say that area equals pi r squared. If I ask you what's the length of an arc that travels one full circular revolution, you would tell me, well, again, that's the circumference of a circle, 2 pi r. And by the way, if I said what's the area of a sector created by an arc that does one full circular revolution, well, you just come back and you tell me the same thing. You'd say the area is equal to pi r squared. If I asked you what was the size of the angle that you just built, you would have told me that theta equals 2 pi r, that's s over r, remember? 2 pi over r equals 2 pi. So no great surprises, hopefully, here. And what we'll do is we're going to do some various revolutions, and we're going to kind of fill in a table. And it's going to lead us to a nice conclusion. A full revolution has an arc length. We'll call that s equals, what? 2 pi r. The angle that's built by this arc is what? 2 pi r divided by r equals 2 pi radians. And the area of the sector, well, in this case, is the full circle, and we know that it's pi r squared. If we did half a revolution, our arc length would be what? Nothing more than pi times r, just half of the circumference. Our radian measure would now be what? Pi over r, pi r divided by r, or nothing more than pi. Hey, not surprised, half that. What would the area of our sector be? It'd be 1/2 pi r squared. If we did a quarter revolution, well, we would find out that our trip, how far will we go? Well, 1/4 of 2 pi, that would be pi over 2 times r. That's how long our trip would be. That's how big that arc would be. We'd have pi r over 2r. We'd get what? Pi over 2 for distance in radians. And gee whiz, what would the area of 1/4 of a circle be? It's 1/4 pi r squared. If we did 1/12 of a revolution, we would travel what? Well, our arc length, our circumference, just as if you did 1/12 of the circle, is 2 pi r over 12, nothing more than pi over 6 times r. What would our value be in radians? Well, we'll find out. Pi over r times 6 pi over 6 r over r. What do we get? Pi over 6. And gee whiz, what would our area be? It'd be 1/12 the area of the first full circle, 1/12 pi r squared. And if we do a little bit of work, what we're going to find is if we know a couple values, we're going to see there's a very nice relationship between these various components. And they translate into the following formulas. If we're given the radius of a circle, r, and the measure in radians of the central angle subtended by our circular arc, we can calculate the arc length, we can figure out what s is, and we can also figure out what the area of the sector is. And it turns out s equals r theta, and a equals 1/2 r squared theta. So over here, here's s. We can figure it out. Full circle revolution. How far did we travel? 2 pi radians times r. Arc length, 2 pi r. And you could work forward with all these. S, theta, and here's our good old a. We know r just goes, as we already put, just work with the letter r. And you'll see for all these different pieces, those formulas hold true. Key piece, for this to work, your angle has to be in radians. It does not work if you're dealing with degrees. So please, please, please tuck that away. Now, what can we do with something like this? Well, we can solve some problems along the following nature. Again, I'll put the formulas up here just so we'll have them. And let's see if we can figure out. Find the arc length and area of the circle formed by a central angle of 2 pi over 3 if the radius of a circle is 6 feet. What do we have in this problem? I know that theta equals 2 pi over 3. I know that the radius of the circle is 6 feet. Okay, so what do we think we'd have here? Sector length equals 2 pi over 3 times 6. S equals r theta. This would become 4 pi. What would the area be? Well, the area would be equal to 1/2 r squared in this case, which is what? 6 times theta, which is what? 2 pi over 3. Sorry about my sloppiness here for a second. 1/2 36 2 pi over 3, which will become 36 times 2 is, excuse me, 36 times 2 is 72. 1/2, 1/3, 72 over 6. I'm going to go ahead and get 12 pi as the area. So let's think about this. Let's just work this problem for a moment. 2 pi over 3. Remember, a full revolution is what? A full revolution is 2 pi radians. So 2 pi over 3 radians should be 1/3 of a circle. Okay, let's do something. What's the circumference of a circle that has a radius of 12 feet? It's 2 pi r. In this case, it would be 2 pi times 6, or 12 pi. What do you notice? Our sector is what? 1/3 of a circle. 4 pi is exactly 1/3 of 12 pi. Okay, we also should have our area that we got. It ought to be 1/3 the area of the entire circle. What's the area of a circle with radius 6 feet? It's pi r squared. Pi times 6 squared, 36 pi. That's what we would have if we had a full circle. And what did we get for our answer? 12 pi, exactly 1/3 of this. So just kind of use those comparisons. Realize that we kind of know, hey, a radian represents how much of a circle. We can figure out the basics of the circle and then just kind of apply that. Just be comfortable working with these. Find the arc length that subtends a central angle of 120 and a circle of radius 5. Well, remember, these formulas only work when we deal with radians. We're going to need to do something with this. I know that r equals 5. And I know that my angle, theta, is 120 degrees. However, 120 degrees isn't in radians. I need to convert this. And remember, our conversion formula says take this and multiply by pi over 180. I'll get 120 over 180, which turns out to be 2 pi over 3. 120 degrees, same as 2 pi over 3 radians. Now I'm working in the right way. Find the arc length. S equals r theta. S equals 5 times 2 pi over 3 equals 10 pi over 3. Last problem. The area of a circular sector with a radius 3 is 24 centimeters square. Determine the size of the central angle along with the arc length by which it is subtended. So let's see what we have. I have A equals 24. I know that R equals 3. Can I use these with the formulas above? I sure can. A, R, the only variable I would need to solve for is theta over here. 24 equals 1/2 3 squared times theta. Take a look. Let's just make sure we're comfortable with this. 24 equals 1/2 r squared 3 theta. 24 equals 9 over 2 theta. Theta equals, I'm going to multiply both sides by the reciprocal of 9/2, 2 9s, 48 over 9. which I can reduce a little bit. Divide each of these as a factor has 3 as a factor. Theta equals 16 over 3. Can I figure out what my arc length is? I sure can. Remember, S equals R theta. R equals 3. Theta equals 16 over 3. S equals 3 times 16 over 3 equals 16. So as you work through all these problems, be comfortable. For the time being, you will have, you're going to have both of these formulas. But be comfortable with what they mean, understanding that your sector is just what? It's kind of part of a circle. Remembering the full area of a circle, pi r squared. The full arc length of a full complete trip around a circle is nothing more than 2 pi r. Understanding these relationships will allow you to work with these formulas. Last proviso, remember, radians only. So this covers the last part of section 5.1, part 2.